Welcome to APEC. It's August 14th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Steve Burns will discuss his experimental replication of Fran Aquino's System H, along with extra low frequency gravity control. Daniel Sheehan and Remi Cornwall will be discussing emerging concepts in retrocausality, along with Maxwell's demon and the second law of thermodynamics. And then after that, Mark Sokol and Jeremy Rys are going to be joining us live from TeslaTech 21 with an overview of this year's conference presentations, exhibitors, and the innovation that's happening there. They're going to be doing some spot interviews as well. Today is going to be a really exciting session. So after that, we're going to try and wrap up the event with open discussion and ad hoc presentations. Just a couple of quick reminders. You can view conference replays, details, and speaker information on our website at www.altpropulsion.com. Please save your questions for after the conference presentation. You can go ahead and type those into chat. We try and go through those after the presenter finishes. And of course, you can also raise your hand and we'll have a giant discussion session there. So I want to take you now to our first guest. Steve Burns is a retired nuclear engineer who joins us to discuss his experimental attempts to replicate Fran Aquino's System H experiment, which was proposed as a method of gravity control via the generation of extra low frequency electromagnetic waves. System H is very well known. It was very big several years ago, and Steve has just been pursuing this diligently for quite a long time. So I'm very excited to have him. He is approaching verification of the System H design, and his experimental apparatus now routinely radiates 4.3 watts at 1.2 hertz using a Gravitronic tuner that he developed. So I want to welcome Steve to today's event, and now I'm going to hand things over to him to get started.
First of all, I just want to tell everybody I'm more Wallowitz than Hofstadter. So if you're looking for a really high level physics discussion, you're probably going to be disappointed. I also want to point out that I'm an engineer. I don't have a theory, and I don't have a dog in the theory fight here. I'm sort of the victim. So I'm really not interested in duking it out with theorists here. So to give you a real quick background of how I got involved with this, back in 1999, I joined the Green Glow list, and someone posted a link to Aquino's work, and I read some of it. And so I posted a message on the list that you might be able to prove this with a radiating antenna. And I immediately started getting emails directly from Aquino. And we emailed every day, maybe several times a day for several months, 3 or 4 months. And we thrashed through systems A through H, where we were trying to build a cognitive framework to try to understand how to use an electromagnetic radiating element to test his equivalence theory. And so systems A through F were basically, we were building a cognitive framework and we discarded them as the learning curve. System G, it was an attempt to use a lower conductivity medium that the antenna element radiated into, so you wouldn't basically short it out, and trying to get permeability as high as we could. And then System H is basically pushing the pedal to the metal on conductivity. And because it is surrounding a radiating antenna, there's a question about how to interpret Maxwell's equations on this. And I personally think that it cannot be insulated. You cannot have an insulated layer there, because if you do, then the insulation becomes the medium and you end up with a coax cable. So the problem with System H is that it would basically just short out the antenna and you just have a conductor. And that's why I keep claiming that you need really a superconducting antenna. And as we'll learn later on, the theory supports the fact that this is probably why Tic Tacs and gimbals operate cold. So I just want to say something quickly about System G. I was involved in the conception of the concept, and I've looked at lots of concepts, and System G is just one of them for me. I was not involved directly with the experiment that was published. All I know about it was, other than the fact of participating in the conception of it, is that the university in Brazil used so I was told that they used a consulting firm in the Southwest US to design the antenna, which actually happened faster than I thought it should have, considering the consultants that I've worked with. I've made a living in electronics for 47 years, so I've seen everything 5 times. The other thing is that there's 3 red flags for me on that experiment. Number one is that I nor anyone else I know has ever seen a photo of it. I've just seen paper drawings. Number 2, the data is really sparse. And number 3, last but not least, the transformer they used a solid iron rod for a high current transformer, and transformer engineers will tell you that it would be no time at all before, at the currents that they had, there'd be no time at all before you get inductive heating and that rod would glow red hot. So those are question marks I've always had about this. And so now you kind of know what I know about that experiment. I received an email from Aquino saying that he was successful. I still have it in the archives. But like I said, that's really all I know about it. So this discussion isn't about that experiment. As far as I know, it's never been replicated. So to me, it's just a data point somewhere that really isn't relevant at this point, and I've moved on beyond it. So I'm hoping that I don't get a lot of questions about it, because I really don't have a lot more to contribute about it other than what's already known. Nodden showed an interest in it. I communicated to him what we had learned from our modeling, and I have to say, Nodden picked it up really quickly, and he posted it on his website, and that's sort of been there for 20 years now. So this thing, to me, I kind of lost interest in it for several years. And I was researching something unrelated, and I stumbled onto Stratton and Chu's research at MIT on prolate antennas during World War II for military radar. And it was a real aha moment for me. And I'll show you that as we get into this. But it was a turning point for me, and I just kept getting interested in it. And I don't really have a passionate interest in UFOs. I read a paperback when I was a teenager in the 60s. I discovered Hill's book in the 90s when I was scanning library shelves. And starting with Keen's documentary a decade ago or so, and then some half dozen or a dozen documentaries after that were actually tried to identify patterns and attributes. It kind of sparked an interest in me again on this, because quite frankly, the theory just gives good answers. And I'll show you why I think that as we get into it. And one other thing I just want to say about it is that I'm not an expert on UFOs. I know what I've seen on TV, and all I can tell you is what the theory says about them. So that's kind of the subject of where I'm going here. And Tim wanted to show a little bit about the experiment. So I made 2 really short videos, one of my setup and one of how I make experimental measurements to hopefully show you how I'm getting numbers. All you have to do is generate, according to my spreadsheet, 25 watts of radiated power at 0.5 hertz and a volume 1/8 of the size of a soda can. So that's easy, right? I mean, any electrical engineer would tell you that you'd have to be a stark raving mad lunatic to even try that. Well, I tried it, and I played around with it for years because I'm retired and too much time on my hands. So I'll show you what I've come up with, and you can make your own decisions about the relevance of it. And let's see what else I got here. It pretty well covers what I was going to say up front. So let me just dive into it here and we'll go from there. And I've never used Zoom before, so I'm going to try to see if I can make this work. Can people see this? You should be looking at a PDF PowerPoint. Is this?
Oh, and again, I think you have to click once more, Steve, to actually display it. It's going to take you to that pop-up and ask you what screen you want to display.
Oh, yeah. Okay.
Yeah, no worries.
Let's try that. We're just going to get this one. We'll get it figured out here. Can you see that?
There we go. Yeah, and
All
that's
right.
the same PDF you had up last time.
Yeah, this is years ago, I had a job interview where I had to give a presentation. So I created this spreadsheet. So I just thought I would just give it here. Don't ask how that turned out. So this is about extremely low frequency electromagnetic gravity shield theory and experimental design. It's Aquino's theory, and I basically injected antenna theory into it. And we came up with a model, and other than his MG equation, it's just basically EM standard textbook equations that everybody would be familiar with in that field. So let's go here. I'm going to skip over a lot of this because I've got a lot of material to cover, and some of it's relevant, some of it isn't. So let me just say that I don't know of any reproduced gravity shield experiment in the literature. I'm going to give a historical account of how we did this, and I'm not going to dwell a lot on the equations. Like I said, they're standard equations, and you can look at this when you want. It's on my website. Google is discontinuing the site's platform in 2 weeks, and I don't have a plan to repost it anywhere. And it is downloadable. So if you want it, you just get on the site in the next 2 weeks and download it. So we're going to try to model an apparatus for theory validation, and then we're going to present experimental efforts to date. So it's all started, at least for me, with a publication. It was back in the 80s where someone assumed from their quantum mechanics analysis that equivalence only holds at absolute zero. And sorry for the phone. And so if you increase temperature where you get thermal radiation, you can see a slight difference. And the key word there is slight. If you don't get down in frequency, it's very, very slight. And so Barton was the paper we were discussing at the time in the late 90s, early 2000s about his rebuttal. And you can see here he has a statement that he couldn't find an error in their conclusions. He just came to a different one. And then Aquino published its work, and this is where I got involved in it. And he basically derived the general case, not just for thermal radiation, but for all frequencies of radiation. And you can download the spreadsheet from my website, so I'm not going to go through all of the stuff here, but it basically just says, we have this equation, and if you put 0 in for U, it reduces to just mg equals mi, as you would expect it to do. So it does reduce properly. And if you take the derivative of it and solve for 0, you'll get a 0 for U at the square root of 1.25. So it does have a 0. And so this is the equation that basically spawned my effort. And if you look at it, it's just Maxwell's parms, basically, where if you do an analysis of this equation, you will find that permittivity has little to no effect on reducing mass. That the main players are permeability, relative permeability, since you're trying to use material science to design something, and conductivity. So those are the 2 players that I focus on in this talk. And I'll show you later on in another paper where a lot of these parms are just phase velocity. And if you reduce it and put phase velocity in here, the equation reduces to a much simpler form. Okay, this is stuff what we did way back where I discovered some data that the Navy took for underwater submarine antennas where they were trying to get them to work, where they measured the phase velocity for salt water. And so I tried to curve fit it to make sure that it was consistent with Maxwell's phase velocity equation, and it fits very well. And down here, I have this little insert on all the slides here to kind of remind us of what we're doing. We have antenna elements. This is a dipole. We have antenna elements where the lighter color here, and then it's surrounded by a medium, which is the gray. And then the outside, you can see the shield that encompasses it. Here's the equation for phase velocity from Maxwell's equations. And I want to go back up here for a minute. There's something that I missed here, I think, and is very important. Here. Nope, I haven't got to it yet. Okay, I apologize for rambling here. So what I contributed was I just took the equation of a monopole or a dipole, depending on the configuration of the experiment, and calculated the radiated power from it. And we determined the efficiency of the antenna based on the ohmic resistance of the antenna. And then we calculated the attenuation through the medium, since you're trying to illuminate the shield. And we ended up with a power density based on what basically is just standard E&M theory. And so now we have to illuminate atoms, and that's a little more difficult to analyze. So Aquino came up, this is what he sent me, came up with a number that I use in my spreadsheet. And again, you can look at this and decide what you think of it. And so when you're all done at the end of the day, you end up with a model that can approximate the value of U in his equation, which is this guy. So we did that. And if you do a mathematical analysis on it, you'll find that this is a MATLAB plot that I did years ago, and it has set parameters for some of the parms. And frequency kind of goes from high to low here, and it starts off at 1 hertz, it goes down to 1/10 of a hertz. So you can see that you don't get a whole lot of effect. And if you take this out to even RF energies, visible light, it's just, the difference approaches Planck's constant. I mean, it's really small. And if you get everything just right, you can come in and you can actually see a null effect. Now, this is an inflection point, but mathematics says that it's just as much of a zero as a null. So I'm just telling you what the model says here. And you get a very sharp mass cancellation. And that's why I say it would be very difficult to stumble onto this inadvertently, because it's just, even when you get things just right, it's hard to get it to zero. And I didn't see the slide here, but it's very important to understand that the theory basically says that the effect is true for both radiating atoms and atoms being illuminated. So you could have an antenna with a high permeability and conductivity that could actually radiate and have mass reduction. Or you could have an antenna that's radiating and illuminating a surrounding shield that produces mass reduction. And later on, I'll show you why the model indicates that tic-tacs and gimbals are radiators and V's and triangles are shields. All right, so let's go on forward here. So we're giving a history here, and I'm showing you that a superconducting antenna really helps out here. And if you do the math on a series resonant circuit at 1 Hertz, you just get ridiculous numbers. You need 25 million henries of inductance to tune a 1 nanofarad monopole. And if you're working with a loop antenna, inductive loop antenna, you need, depending on the inductance of the antenna, you certainly need at least more than 10 farads of capacitance. Spoiler alert, supercaps don't work, they're too leaky. All right, so showing you a gyrator here. If you look at it, the forte of an inductor is it resists changes to current. So if you put a step function in here and try to change the current through this resistor, this would be the series resistance of the inductor. For a step function, capacitor basically passes it as a dead short. So the same input is put on both inputs of the op amp. So basically, you put an output equal to the input, and you have no voltage change across the resistor instantaneously, which means you have no current flow. It's resisting the current flow change. And then as the capacitor charges up, it allows current to flow through the resistor. So it just mimics an inductor. And this shows you the size of the inductor. So if you do the math here, you'll find out that you need ridiculously large values of components to get down to 1 Hertz. So I've had to come up with all kinds of innovative ways to trick it to get there. And this just briefly shows that Naudin's effort where he tried to do it, and then there was a French effort at the same time almost where they tried to do it. Both of them failed. And I just have some ideas here of what to do next. And this is like 20 years old now. Okay, so let me go to another plot here, see what I can find. Well, actually, I don't think I need to. My Zoom control is up with my paper, so I got to minimize it here for a second. Okay, so this is a paper I wrote in 2005, right after I discovered Stratton and Chu's work at MIT. I wasn't looking for it. I really had lost interest in this, and I was scanning the library for another project, and I was looking at a book, and it had Stratton and Chu's results in it, and it was really a game changer for me. When I saw that, I just went, wow, this could actually explain tic-tacs and gimbals. So let's go through here. Again, this is all on my website, but it shows the derivation of it. And here's the same equation you saw before, only VP is replacing all the parms that you saw. So it's much easier to understand it with this. This shows where the 0 is, and then this shows what VP is, which is all the parms that made the equations more complicated. And so you can, read through this and see. And I actually took something from Stratton and Chu, and I actually tried to make a gimbal. So, and you'll see why later, why I think gimbal is a saucer. I'll show you why the theory points to that. So at any rate, anyway, so a lot of this is just, I was thinking out loud, and it's just mental dribbles. So you can digest it if you're in the mood. But we get down here to the part that I think is actually relevant, and it's showing you that for a prolate antenna, whether or not a sphere is stretched into a cigar or squashed into a saucer, they pretty much act the same according to data that was taken at MIT. And they have a natural resonance. And that means you don't have to tune it. So you don't have all the complications of these far out components that you can't realize. And the ratio turns out to be length to height of 7 and a length over lambda of about 0.5. And so I go through an example here where I start out with that, and then I go, and of course the radiation resistance of a resonant antenna you expect to be about 72 ohms, and that's what they measure. And so I go through a whole bunch of stuff here that says this is how you would make a tic-tac, excuse me, a gimbal. And then you would come up with this. And then I'm showing you how to use a capacitive multiplier to tune it if you turn out to be just a little bit off of resonance. And so it's all here if you want to dive through the details. And then at the end, I plot for that particular design what voltage would have to look like in order to tune it to zero mass. And so you see for this design, you need high voltage. And this is what the control curve would look like. Whereas over here, you're on the other side of the 0 point. And I'm not really sure what this is. So I'm going to leave it up to other people that are smarter than me to figure out what happens if you go through 0. And so this is just another gyrator. It has a buffer stage in here, which is what I use. And so then I go through an appendix and I show you textbook stuff that I probably should have left out. And I was just trying to derive some of the equations. So I'm just going to go down here and I'm going to show you Stratton and Chu's work, which I think is just amazingly significant. I don't know that I can zoom this, so I'm going to have to do it piecewise. Okay, they start with a sphere where D equals L. You either squash it into a saucer where L is the length of the saucer and D is the height, or you pull it into a cigar. And keep in mind the extreme cases of this is just a flat circular plate and this is just a wire. So you're approaching that. So this is the feed resistance. I'm going to do this last. Let's look at the reactance curve. It says transaction from sphere to thin spiral wire dipole, resistance and reactance of spiral antenna fed at the center from Stratton and Chu. And I apologize for the poor quality of this. I was using someone else's scanner and I didn't really know how to use it. So if you want to see it firsthand, it's reference number 4. And I even give you the page number. All right, so let's go back down to the reactance plot and let's take a look at it for a minute. So this is plotting L over lambda and reactance. So you can see you got a resonance. So let's see what that means. Well, this is L divided by D, and this is 7,070. This is 707. This is 7.07, and this is 7.05. So from here to here, you have hardly any change. So what I'm interested in is from here to here. So the larger the number, the less height you have in the device. So if you're going to have headroom, you're going to have it really long. So 7.07 kind of gives you the optimum value of giving you as much headroom as you can per length, but you still end up with a 7 to 1 ratio of length to height. And if you can achieve that, it's saying you can get zero reactance if you have L over lambda equal to 0.5, which are the params I used in my design example. And if you come back up to the feed resistance chart, it shows you for 7.07, it's about 73 ohms. So it just seems to make sense. And these are what the curves you get for the larger ratios. And this is 7.05 again. So I adopted 7.07 for my standard ratio for what I talk about. But again, it doesn't have to be that. It can be larger. So that's basically what this paper says. So let me go forward here and see which one do I want to do next. Do I want to try to convince you of what the glow is? No, let's do advanced first. Okay, so I did this in 2011. I had not seen the Navy videos when I did this. I didn't know anything about them. So I went through and I analyzed what I had seen on television. And again, I really didn't pay much attention to what I call he saw, she saw shows because they're repetitive and you don't get a lot of information from them. I think Keen was the one that started this and that got me interested anyway, where she actually tried to document attributes. And so I started thinking about that, and I started trying to piece together what I thought this theory says. So you can come to your own conclusions. And if you look at Stratton and Chu's work, you'll find that if you can get these things to radiate at an extremely low frequency where you can bring yourself down in mass, that they will basically do specific things. And one of the things that I think is important is if you look at the radiation pattern of a sphere, and I'm not an EM guru. Whenever I do dot and cross products, I get a migraine. So I'm hoping that other people can maybe spend some time with this and polish it off. But at any rate, the radiation pattern for this type of geometry, for a prolate cigar, you tend to have the highest radiation pattern at the tips. And for a saucer, it tends to be in the middle of the circle. So these are the places where gravity is going to be affected first, because you've got enough radiation to bring it to that level that the theory demands. So with that said, I would say that if you're looking at something you can't identify in the sky, that this is what I would expect to see at first. And so I'm just pointing that out. And again, if you study the theory, you'll find that you can reduce mass 8-10 orders of magnitude. So if you believe in conservation of energy, which I do, and you believe that if you do reduce mass and you've got a velocity, initial velocity, that doesn't matter if you use conservation of momentum or conservation of or kinetic energy. One goes as a direct multiplier, the other is a square root. It's still a very impressive startup velocity, just blows you away. And it can happen very quickly. And of course, you don't have, inertial mass or gravitational mass, so you don't kill everybody inside, theoretically. So I'm just saying that that could explain fast acceleration. And I'm also pointing out that this is where it gets, for me at least, it gets a little more, you got to have faith in the theory, and that is, people smarter than me could figure this out in detail, but the way I look at it as an engineer is we basically live in an analog universe, that the sun doesn't pulse on and off. And analog implies curvature, and curvature implies distance. So it's not, at least for me, unreasonable to believe that you could have a mass reduction extension beyond the outside surface of the craft. As a matter of fact, it would surprise me more if it didn't do that. So with that said, if you're reducing mass and you're speeding up things to conserve conservation of energy, then the atoms and molecules in the atmosphere won't be any different. And I have another paper where I try to use Lamour's equation for accelerating charged particles to show you that you could possibly explain the glow with that phenomenon. So I'll wait and get to that later. Just have faith right now that it might be explainable. So let's see what we got here. That's acceleration. I show the same plot here that I showed in the other paper. So where are we with architectures? Well, if you look at the different varieties of what I think of as the more credible observations, and you try to put them into patterns, I think you could say that a lot of them seem to be configurations of prolates. So here I have a outer shield, which would be the black, and I have saucers inside that are radiating into the shield so that the shield reduces mass and simply becomes a carrier for the saucers. So you basically have a vessel that can transport other vessels. And if you keep going with this, here I'm showing, I'll show this later, but I'm showing what I think the theory says a prolate cigar would look like, even though it doesn't show the structure of the radiation pattern, which I will try to convince you that gimbals and Tic Tacs have. All right, so we'll get to that in a minute. So, you know, you could have a line craft with 3 Tic Tacs. Here's a drawing where I did with Visio, where it made the length to the height of the prolate 7.07, like Stratton and Chu's work. It's all based on that. Here's the end view showing what it looked like from the end. Here's a V craft, same concept. If I was writing science fiction, I would have the back ends of these things open up, and the saucer just stays stationary in the shield. And 12 Tic Tacs could just unload, go off, do their thing, come back, rendezvous, and thing would take off again. It's a thought, but at any rate, if you do the 7.07 for cigars and saucers, you get something that could actually be, in my opinion, presented as what was observed. And again, you can, draw your own conclusion from this. This is not my theory. I've been interested in it because it just gives me interesting results, and you can draw your own conclusions from it. I'm not going to try to change your mind or anything. All right, so let's go down here. This is one I showed before. And then, of course, now this one I pulled from Keen's first television documentary. I actually froze it on the screen and did measurements. And I heard later on that it was a hoax. But I really don't keep up with UFOs, so I really don't know the story behind it. But I'll tell you, it fooled me. I thought that the plasma patterns underneath were reasonable, and so I wanted to see if the model would describe it. And even though the plasma location on the bottom of the craft was kind of in the wrong place for me, I just went with it, and I didn't try to fudge it. I don't fudge anything. It's either it explains it or it doesn't. So this is a little off for me, and I really didn't understand that. But anyway, you could kind of get your head around how you could make a delta craft, but clearly a triangular craft makes more sense. And I think that's what could explain them. So they would be basically a 3 Tic Tac carrier with a gimbal module that stays with the shield. And that's pretty much it for this. I tried to give references where I got things from. The pointing vectors for the antenna pattern is here, if you want to look it up. So with that said, let me go out and really get into the iffy mode here and try to explain what I came up with to describe glow, what I call glow. At first, I tried to explain it with ionization radiation, and I really wasn't happy with anything that it said because I just couldn't believe it. And then I thought, well, gee, let's try Lamore. And then it really started to make sense to me. And so again, you can read this, it's on my website. And I basically go through an analysis of what Lamore would say about this. And you can see his equation. It doesn't care about velocity, it only cares about acceleration. So if you reduce mass quickly and you accelerate quickly, something's going to radiate. And from linear accelerator measurements, it's been determined that the radiation comes from the accelerator power supply. There's no free energy. It's about a 15% overhead, and therefore I'm claiming that Tic Tacs would use more power in atmosphere than in the vacuum of space because they have to have this overhead of the glow. And so I go through an explanation of why I think that it could change size and change color. And so I also believe that if it does accelerate and it gets to a fairly high velocity and it impacts the surface of the shield, which is most likely metal, then you would get soft X-rays out of it from Grimstral. It's the same concept as your dentist X-ray machine. And you could actually use the X-rays to characterize the constituents of the shield, which would tell you how they make it. So that's what that's about. And so here I have an artist's view, which actually I made this with Visio, and showing you what it might look like according to this theory. And again, I stay interested in this theory because it just gives me interesting results, and I don't think that anybody could have discovered it inadvertently, because even when you know how to do it, you can't do it. So let's see what else I got here. So what I'm going to do is, now that I've said that, I'm going to try to I'm going to try to change to different screen. Can everyone see this?
Yep, looks like it worked perfect.
All right, well, okay. Now, I'm not making this up. I did this morning. It's the first time I've ever done it. Last night I had the thought, well, I'm going to talk about, radiation profiles and patterns. Let me just take a quick look and see what gimbal and Tic Tac looks like. Go Fast is so small, it looks like a saucer, but I didn't include it because it's just really tiny. So what I did here was I just captured the Navy video. You can see the bars from the video over here, and I zoomed it up by 400% just so I could work with it. And then over here I did a different picture enhancement effect so I could see the outline a little bit better. And here I used a different effect for a different image I captured in the same video. So I've got two images captured in the same video. And just looking at this, you can kind of see that the profile dips in the middle, sort of like what I was trying to show in that last, the PDF that I was showing earlier. So you have to remember that the prolates go down to a point here. So any large amount at the tips would kind of get averaged out with the higher radiation magnitudes at the top and bottom. But you can still see there is some kind of structure here which says most of the radiation is coming off from the tips of the object. So I'm claiming that this theory says that this is a cigar. Now let's look at gimbal. Again, I did the same thing. I just took a snippet of just the part of the video that had the object, blew it up 400% just so I could work with it. And then I did an enhancement on it. It didn't change anything other than I just did a photo effect on it so I could see the outline better. And again, you see, as with the saucer, the radiation pattern is highest at the center, tops, and bottoms, just as the EM theory predicts it would be for a prolate saucer, and that the outline seems to indicate that that is the case. So I'm claiming that the theory says that gimbal is a saucer based on this profile of what I'm calling an extended mass reduction zone that goes slightly beyond the surface of the craft. So with that said, let me figure out if now I got two short videos here. One is of my setup, and it's just a corner of my man cave, and you're going to find that I don't have a lot of high-tech equipment because, see, everybody's falling asleep here, which is typical for me. I don't have a lot of high-tech equipment, mainly because nothing works below a hertz. So I just use circuit theory to do most of it, and I explained to you how I do that. So let's see if I can actually get a video to work here. I don't know that I can. Can you see this?
Steve, it's actually showing, let me see, gimbal.jpg. Is that the one you're trying to show?
All right, well, it's not working then. All right, let me see if I can figure out how to do that. Movies, TV, let's try that. Did that work?
Yeah, no, works perfect.
Okay, I'm going to start it over. So you can see this, right?
Yeah, and it looks like we can hear it a little bit, but it's not sharing the audio. It's just kind of a feedback on the audio. So
sine wave generator, voltmeter. Sine wave generator goes down to a millihertz. Gravitronic tuner, which is a work in progress, and you can see it's experienced feature creep, and I don't polish things off. I just use them as they are. Power supply in the back where I can change for higher current. Terminal block where I make changes. Here's the capacitor I'm using for the demo for my capacitance multiplier. It's an inductive loop transistor, radiator. 4 half-ohm resistors that I can tap off of to make the ESR, the capacitor, what I want, and then 4 10th-ohm resistors that I can manipulate to make the ESR as low as I want. And if I get low enough, at some point, the electronic bursts into flames, and I don't know exactly where that is yet. And then the back side over here, it shows the radiator, and I use a little clip that got put right on the wire of the device under test, and it goes into a follower with gig ohms of resistance, so I don't load down the measurement. And that's basically what I got. So let's see if I can figure out how to do the other video. Give me a few minutes. I apologize. I've never used Zoom before, so I don't quite know how to.
There we go. Looks like it's playing now.
Can you see it?
Yeah.
Oh, good. Can you hear it?
Not really. So it's kind of a Zoom bug, but the noise coming through your speakers comes back into your mic just a little bit, but not really enough to hear what's going on. It's not doing the actual direct sound from the video. It doesn't play that.
Did it go away, the audio? Yeah, did the audio go away?
No, it's still there a little bit.
I tried muting it, but I muted myself here. It's just a scope. The left side's a oscilloscope, the right side's a spectrum analyzer. I have a frequency indicator down here, and voltage RMS is over here. And I'm going from 0 to 10 to 20. Let me just, you may have to minimize your Zoom screen here to see it. But what I'm going to do is I'm going to start at 20 hertz, and I already know that the resonance is just under 10 hertz. So I'm going to start at 20 hertz. I'm going to move down. I'm going to show you the resonance, and then I'm going to go down even further and show you that it is a resonance. And I'm going to go back to the resonance. And theory says at that point it is basically Ohm's law because you canceled the reactance. So then I'm going to do measurements on the device under test and calculate the radiated power on it. So here I'm powering up, and I always let it stabilize because I've got two high current amplifiers connected together across a small resistance. And so here I'm starting out at 20 hertz, above 20 hertz, and I'm going to move down in frequency. So I'm moving down in frequency, and you can see it gets lower, not by much, but somewhat. So I'm claiming 9.7 is about the middle of the resonance curve. $224 millivolts is the magnitude peak of the spectral energy. So now I'm going down in frequency again, and I'm hopefully showing you that it goes up again. So you'll believe that it's actually a resonance. So I'll go down back to the resonance and hang there for a minute. So now what I'm going to do is I'm going to go to the other side of the device under test, and I'm only going to measure the voltage drop across the capacitance multiplier. So if I subtract the two, I should just get the voltage across the inductive loop antenna. So that's where I'm headed here. A little bit lower, a little peak. So I'm going to go down and measure the lower peak. So if you subtract the two, you get about 30 millivolts across the inductive radiator. And I know that by design, I know that the ESR, the equivalent series resistance of my capacitance multiplier is 1 ohm, because I set it there because I wanted lower current to do this demo. And so for Ohm's law, you have 193 millivolts with 1 ohm, you get 193 milliamps. So that's how much is flowing through the series string at resonance. So now I know the current through the inductive radiator, and I know the voltage drop across it. I can calculate the radiation resistance. And I know that by measurement that my 9 inches of 18 gauge wire has a ohmic resistance of about 150 microohms. So if you do the math for 200 milliamps, you'll find out that the voltage drop is negligible. So I'm claiming that the voltage drop I'm seeing is across the radiation resistance. And if you do the calculation, you get, 5 milliwatts or so, a little higher maybe. But remember that this is Ohm's law and power goes up by the square of the current. So if I go from 200 milliamps to 2 amperes and the tuner's good for 4 amperes RMS, you'll be close to a watt. So here I am at watt at 10 hertz. And I really haven't even gotten started with it. So what I'm saying is that the gain of the capacitance multiplier is set to unity. So I'm just reading the lowest value of capacitance, and I'm getting a 9 point something hertz resonance. So if keep in mind that the resonant frequency goes by the reciprocal of the square root of the capacitance. So if I increase the capacitance by a factor of 100, I can go down in frequency by a factor of 10. So now I'm down below a hertz. And if I increase my capacitance by a factor of 10, which I can do easily, that takes me down another factor of 3. So now I'm down below a half a hertz. So that's how I go down in frequency. And then it gives me just a little window where I have to search for the resonance rather than a whole wide range of frequencies. So this is the way I'm operating it right now. So that's pretty much it for the video. So that's pretty much all I have. I was just showing you basically why I'm interested in this theory and how I'm doing measurements to try to see if there's any way I can verify it. Quite frankly, I think that to do this without a superconducting antenna is a long shot. But I just want to see how far I can get with it. So that's basically where I'm at. What I would hope is that somebody out there has some kind of interest in it where they would pick it up and maybe try to contribute also. But that's all I really have, Tim. So you can take it away here. I'm willing to try to answer some questions. Like I said, I'm not a theorist. I'm an engineer by training. Nuclear engineering is exactly what it says. Engineering. We don't do quarks and muons. We're more about neutrons and gamma rays. And so while you guys are asking me questions, I'll give you a pop quiz. The center of the sun. Pardon me?
Oh, wonderful. Well, Steve, let me do this then. The first thing I want to do here is I want to put this on gallery mode, and everyone please give an enormous applause to Steve Burns. Thank you very much.